In this mini lecture, we're going to talk about relating intensive properties. Let's first remind ourselves what intensive properties are. Remember, we have two types of properties: extensive properties, in which the value for the overall system is the sum of all the parts into which the system is subdivided. In other words, it depends on the size or the extent of the system. Some examples would be mass, volume, or energy. By comparison, the intensive properties, their value for the overall system is not the sum of all the parts. In other words, it can vary with position within the system. We're going to run into a lot of intensive properties. Some of them are specific volume, pressure, temperature, specific heat, specific internal energy, specific enthalpy, and specific entropy. The question is, how do these relate? And it turns out that the state principle tells us how many of these properties we need to know to fix a state. So to fix a state, we need one independent property, that's one independent intensive property, for each way that the system's energy can be varied. So if we take a simple closed system, we have no mass entering or leaving, we can define a system boundary, and there are two interactions, heat and work. So, because we have two interactions that can change the energy of our system, we need two intensive properties to fix the state. And all of our other intensive properties can be determined using some other property relation based on the two that we already know. Three intensive properties that tend to relate to each other a lot are pressure, specific volume, and temperature. We call the relation the equation of state. Turns out that for most substances, it's very complicated. Here we have a graph of the pressure, specific volume, and temperature for a substance. You can see that there's a lot going on. You've got regions where the material is in different phases. A phase is a substance that is homogeneous in chemical composition and physical structure. By physical structure, we mean solid, liquid, or gas. You can see on our surface that there are different regions. We have solid, liquid, and vapor. In addition, we have regions where we have mixed phases, where we have solids and liquids acting together, or solids and vapors coexisting, or even liquid and vapor coexisting. If we look at this surface now from the pressure and specific volume end, it collapses to a single 2D plot that we call a PV diagram. And here, once again, we can see all the different phases: the solid-liquid phase, the vapor phase, and the mixed phases. An important thing to notice is that in the solid region and in the liquid region, big changes in pressure mean very small changes in specific volume. And so we call this an incompressible substance, in which the specific volume does not really depend on the pressure very much. On the other end, in the vapor region, you can see that as we move away from the vapor dome, the curves become nearly linear. And in that region, we have what we call an ideal gas. The mixed phase regions, solid-liquid, liquid-vapor, and solid vapor, are outside of the scope of this class, but they're very interesting and you'll be interacting with them in the future. In the incompressible and ideal gas regions, it turns out that we can actually write an equation of state that relates the pressure, specific volume, and temperature. For incompressible, the equation of state is very simple. It's just that the specific volume is constant. For an ideal gas, out in the vapor region, we have an equation of state that says that the pressure times the specific volume is equal to the gas constant times the temperature. We'll be working with a lot of substances from these two regions and using these two equations of state to analyze the systems throughout the remainder of this course. That concludes the mini lecture. Thanks for tuning in and have a great day.